Good morning, students. In the last class we discussed design of synchronous counters using T flip-flop, and in today's class we will see design of these counters using JK flip-flop, right? So before we start the actual design, we need to write the truth table of JK flip-flop. From that we are going to discuss, we are going to develop the application table. Then we need to fill the excitation table. Okay. So first we'll write the truth table of JK flip-flop. Truth table where there are two inputs for JK, J and K, and two outputs Q and QR, 0 0 0 1 1 0 1 1, right? So flip flop is going to remain same when remains in the previous state when J and K are 0. This is called the previous state, or you can say the no change of state. Next, when K is high, Q is 0, Q bar is 1. When J is 1, Q is 1, Q bar is 0. When both J and K are high, the flip-flop is going to toggle, right? If the previous state is 1 0, next state will be 1 0 1, or if previous state is 0 1, then next state will be equal to 1 0, right? So from this we are going to generate the application table. For application table there are three inputs J, K and Q, and we are going to fill the next state column here, right? So J and K are the normal inputs and Q is the previous output, right? Since there are three inputs, we can write total 8 combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, and finally 1 1 0, 1 1 1. Okay, so when J and K are 0 0, see in this truth table, when they are 0 0, the flip flop is going to remain in its previous state. What is the previous state here? It is 0, so next state will also remain equal to 0, and here previous state is 1, so it is going to remain as 1. Next, when K is high, whatever may be the previous state, the next state will be equal to 0 0. If J is high, irrespective of the previous state, the next state will be is equal to 1 1, and when both J and K are high, the previous state is going to toggle. If previous state is 0, next state will be equal to 1. If previous state is 1, next state will be equal to 0, right? So from this we are going to generate the excitation table. The final table, what I told in the last class and last to last class, that was transition table, right? So excitation table is going to be developed from the application table, right? So make a correction over there. Next, to generate the excitation table, we are going to write the values of J and K depending on the values of Q and Q plus. So Q and Q plus are going to be identified from the application table, right? So there are two inputs Q and Q plus. We can write total 4 combinations: 0 0, 0 1, 1 0, 1 1, right? So these states we are going to identify in this application table. So 0 0 0 0 here, right? So what are the values of J? For this combination, J is 0, and here also J is 0, so J I will write as 0. Now K is 0 and K is 1 here, right? So for the K value we are going to write we don't care, because it is changing for the same values of Q and Q plus, but J is not changing. It is going to remain same. J is 0 for this combination as well as this combination. J is 0, so we are going to write J as equal to 0, but K is changing. K is 0 here and K is 1, so we are going to write K as don't care. Similarly, for 0 1, identify where it is 0 1. Q is 0, Q plus is 1, and Q is 0, Q plus is 1. So for these two combinations, J is 1 and K is again varying. So K value is equal to don't care. So K is 0 here and K is 1 here, so it is going to vary. So we are going to write K is equal to don't care. Next 1 0, q is 1, q plus is 0, and here 1 0, right? So what is the value of j? J is varying, so its value is going to become don't care, and k is 1. K is 1, we're going to write it as 1, and the last combination for 1 1, 1 1 and 1 1, right? J is varying, so j becomes a don't care and k becomes 0, right? So this is called the excitation table, right? So with the help of this excitation table, we are going to fill the last table, which is called the transition table, right? So here we are designing a mod 4 counter. So many flip-flops we require? We require total 2 flip-flops, right? So write that 4 in power of 2, whatever power you get, that many number of flip-flops we require, okay? Transition table, okay? Final table is now transition table, right? So we are going to fill this transition table with the help of excitation table, right? So transition table is going to contain the previous states. The previous states are denoted as Q2 and Q1 because there are 2 flip-flops. The outputs of 2 flip-flops will be equal to Q2 and Q1. So next state of these previous states are Q2 plus and Q1 plus, right? So depending on these values, we are going to write the values of two inputs of both the flip-flops, that is J2 K2, which are the inputs of first flip-flop, and J1 and K1, which are the inputs of second flip-flop, right? So now mod 4 counter, the counter value starts from 0 0, next value is 0 1, third value is 1 0, the last value is 1 1, right? So after 0, what we will get is 0 1. Next state will be after a 0th state, next state will be equal to 0 1. Suppose the previous state is 1, the next state will be equal to 1 0, third state will be 1 1, and the last state after 3 we will again go back to the initial state, that is 0 0. Now we are going to fill the values of j and k depending on this excitation table, right? So just identify what are the values of q2 and q2 plus, right? So for first combination, q2 is 0, q2 plus is 0, right? So where is that in the excitation table? The first row. J is 0, k is don't care, right? Next 0 1, it is 1 don't care, 1 don't care. Next 1 1, don't care, 0, and the last one 1 0 don't care, 1, right? Similarly q1 and q1 plus are used to fill the columns of j1 and k1. 0 1 1 don't care, 1 0 don't care, 1 0 1 again 1 don't care, and 1 0 don't care, 1, okay? So now we are going to write the K-map for J2, K2, J1 and K1 to generate the Boolean expressions. K-map for J2, okay? There are 2 input variables, so we need to put the 2 variable K-map. So inputs are Q2 and Q1, fill out these cells, okay? So J2 for 0 0, J2 is 0, for 0 1, J2 is 1, for 1 0 it is don't care, and for 1 1 also it is don't care. Now we can combine this one along with this don't care by treating that don't care as 1, and we can put them in one group, right? So what is the expression for J2? It is equal to Q1. Now K-map for K2, so here Q2 Q1 0 1 0 1, right? So for 0 0, what is K2? 0 0, it is equal to don't care, 0 1 don't care, 1 0 0 1 1 1, right? Again we are going to group these 2 cells. So again the value the expression for K2 is going to remain same as J2, which is Q1, because we are going to group the same cells. Now J1 and K1, all are high. Okay, it is very simple to obtain for J1 and K1 without putting K map. Also you can say what is the expression for J1, right? So 0 for 0 0 it is 1, for 0 1 it is don't care, for 1 0 it is 1, and for 1 1 it is don't care. That means I can put all these cells in one group, and we can write the J1 expression as 1. Similarly, K1, there is no 0 for any of the combination for K1, so I can also write without putting K map. From by referring the K map of J1, we can also write the value of K1 as 1. Now we are going to generate, we are going to put the final circuit, right? So there are two flip-flops we require. The inputs for first flip-flops are J2 and K2, output is Q2. J1 and K1 are the inputs for second flip-flop, and output is Q1, right? So now according to these Boolean expressions, J2 and K2 are going to remain same, that is Q1. So I can short J2 and K2, and I can connect Q1 to this shorted line. Next, Q2 will be equal to 1. Sorry, will be the output. J1 and K1 are again shorted because the expression of J1 and K1 is same. So this is going to be connected to either VCC or in digital you can call it as 1, right? So now how many inputs for how many flip-flops we require? We require just 2, and both the control inputs are shorted and connected to common signal called clock, and this is Q1, right? So if you analyze the circuit, and you will just analyze the circuit, I'll leave it to you. Analyze this part, I'll leave it to you. Just verify whether it is going to output these states or no. After 1 1 you check whether it is going to reset or no, right? So this is the design of a mod 4 counter using JK flip-flop. Okay. Similarly, we'll move to the next slide where we are going to generate design one more circuit, mod 5 you can say, or mod 6 you can say, using JK flip-flop, right? So if I say mod 10, then how many flip-flops you require in that case? You require total 4 flip-flops, right? So in the next slide we will discuss the design of mod 6 counter using JK flip-flop. So in this slide I had rewritten the excitation table of JK flip-flop. Next we'll fill out the transition table. Okay. So there are 3 flip-flops we require for mod 6 counter. So now with the help of this excitation table we are going to fill out this transition table, right? So identify the first inputs, first set of inputs, that is previous value which is Q3, and the next state value which is Q3 plus. For 0 0 it is 0 don't care, for 0 0 it is 0 don't care, for 0 0 again it is 0 don't care, for 0 1 it is 1 don't care, for 1 1 don't care 0, for 1 0 it is don't care 1. Next 0 0 J2 and K2, 0 0 0 don't care, 0 1 1 don't care, 1 0 don't care 1, 1 1 don't care 0. Next, sorry, I made a mistake, wait. So when you are filling out this transition table, so always mark the inputs like this, right? So it will avoid the confusion. So what I'll do, I'll mark this column and this column. 0 0 0 don't care, 0 1 1 don't care, 1 1 don't care 0, then 1 0 don't care 1, 0 0 0 don't care, and the last one again 0 0 it is 0 don't care, and finally this one dashed box. Okay, I'll mark like this. Even when you are writing in the exam or internal, you mark these columns so that you will not be under confusion. Okay, 0 1 1 don't care, 1 0, don't care 1, 0 1, 0 1, 1 don't care, 1 0, don't care 1, 0 1, 1 don't care, and the last one 1 0, don't care 1, right? So all the cells of J1 and K1 are 0, and for remaining, sorry, 1, either 1 or don't care, and the remaining two combinations 1 1 0 and 1 1 1, we are going to fill up don't care in those cells. So no need to put K map for J1 and K1, directly you can write J1 equal to K1 is equal to 1, right? So for other 4 inputs J3 K3 and J2 K2, you need to put K map. So first we will see K map for J3. K map for J3, this is Q3 Q2 Q1, 0 0 0 1 1 1 1 0. So there are 3 inputs, we have to put 3 input variable K map. 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1 1. Next 1 0 0, don't care, 1 0 1, don't care, and for other combinations put don't care. This one is combined with this don't care, and we can write J3 is equal to Q2 into Q1. Similarly, we'll put K map for K3. This is K3 K map, 0 0 0 1 1 1 1 0 0 1. This is Q3 Q2 Q1. All are don't care. For first 4 combinations it is don't care, 2 3 4 it is 0, 5 it is 1, and for 6 and 7 put don't care. Now this 1 can be combined with these 3 don't cares, and we can make 4 cells group. And what is K3? It is Q3 is complement to each other, Q2 is also complement to each other, so Q3 is equal to Q1. Similarly, for J2, put K map for J2. Inputs are Q3 Q2 Q1, 0 0 0 1 1 1 1 0 0 1. So 0 1, don't care 4 0 5 0, other cells 0 don't care. These two cells ones can be combined with 1 0 1, we are putting for J2, no, it is 0, sorry, wait, 0 0 1, don't care 4 5 is 0, and don't care. This one can be combined with this only don't care, and we can write J2 as what? Q3 bar and Q1, Q3 bar Q1. And finally we will put a K map for K2. Inputs are Q3 Q2 Q1, 0 0 0 1 1 1 1 0 0 1, right? K2 don't care 0 1, don't care, and this one. So these are the same 4 cells which we combined for K3. So what is K2 expression? K2 is also going to remain same as K3, which is equal to Q1, right? So now with these Boolean expressions we are ready to design the final circuit. So this is the final circuit of mod 6 counter using JK flip-flop. There are three outputs, Q3, Q2 and Q1. So analysis part I leave it to you. So you please analyze the circuit and make sure that all states are you are getting without any error. Okay, and this is the common signal called clock. Okay, so with this I'll finish this class. I finished the design of counters using 3 different flip-flops, and we are left with only one flip-flop, which is SR flip-flop, that we will see in the next slide.